Hey everybody at the HUSTEF 2021 conference. I hope you're having a great time so far. Thank you for joining my talk on mutation testing for fun and profit, improving the quality of your unit tests. My name is Bas Dijkstra and I'm the Director of International Academy at Inspire Testing. So testing is pretty much everywhere nowadays. We test in development, we test in production, we test throughout the whole software development lifecycle. Testing isn't just an afterthought anymore, and we do it all the time, really. And a lot of that testing is supported by tools, or as you're probably more familiar with, by test automation. And as a result, companies, teams, individuals are spending a lot of time and effort and therefore money on writing automated tests. And that's all well and good, but I can't keep wondering who's guarding the guards themselves. We spend so much time writing automated tests to get more information and get information in a more efficient manner about the quality of our applications. Yet I don't think we spend enough time looking at the quality of our automated tests. These automated tests, they are our safeguards. They allow us to refactor without fear. They allow us to implement continuous integration and continuous delivery, because at each stage in our delivery pipeline, automated tests are executed to get information about the quality of our application. Yet we often do not know a lot about the quality of our automated tests. And I think that's a problem, because these automated tests, they can deceive us. Just having a set of automated tests running at any point in your continuous integration, continuous delivery pipeline, just having those automated tests by themselves doesn't guarantee you that your application actually is of sufficient quality. Automated tests can lie. They can deceive you. They can tell you things that aren't there. They can hide information that I think is really important and that you should really know about. And there are two fundamental ways in which our automated tests can deceive us. The first way is by means of false positives. And false positives, the definition that's typically used for false positives is a test that fails when your application works as expected. So it means that your test shows a big red X, or it's marked as failed, but there is no actual defect in your application. These false positives, they present themselves in two ways. You've got tests that fail continuously, that keep on failing every single time. And my answer to that question is, why don't you fix it? Or maybe delete it, because obviously that test isn't generating any useful information. The only thing you get from that test is noise. So it's probably a good idea to either fix the test or just throw it away, because it doesn't do anything useful. The other way in which false positives present themselves is intermittently, or every now and then. And those tests are often called flaky tests. So tests that sometimes fail, sometimes pass, and you can't really get to the bottom of what is exactly causing my test to sometimes fail and sometimes pass. Now, there are three main causes, at least from my experience, for these false positives. There can be problems with test data. So maybe you're relying on data that's not always there in your system, or creating the data at the start of your test is maybe not as reliable as it should be. It can be a problem with the test environment. So maybe the application that you're testing, or the piece of code that you're testing, is relying on a different piece of code or a different component or even a different system that maybe isn't there at the moment you're testing. It's just unreachable, or it's not behaving in the way you expected it to behave. So that's also a very common reason for false positives. The fact that you're communicating with a different component, another system that behaves a little different from what you expect it to do. And the third cause for false positives are problems with timing or synchronization. So examples of that would be systems that take a little bit longer to send a response back to your application before a process is continued, or a web page that takes a little bit longer to load than you originally accounted for when you were writing your test. So those are false positives. The other way in which tests can deceive you is by false negatives. And false negatives are tests that pass, so they show these nice green check marks, but they fail to detect a defect or an anomaly that's actually present in your code or in your application. And while false positives are annoying, again, they generate a lot of noise. They scream failed test, failed test. These false negatives, these are the silent killers because they don't make themselves known. They don't show themselves, well, hey, something's wrong here. They just keep on passing. They keep on saying, well, I passed the test, I passed the test. But what they forgot to tell you is, yeah, but I didn't tell you anything about that bug that there is in your code. So let's look at an example of a false negative and how they can be introduced into your test suite. So we've got a small Java class here which represents a car with a single property called horsepower, which is an integer. And a public method is a powerful car that returns whether or not this car is a powerful car. And I've written a single test also in Java that creates a new car with a brake horsepower of 200, and my test checks that this car is not a powerful car. It asserts that the result of the return value of the is a powerful car method is equal to false. Now, it doesn't come as a surprise to you, probably this test will pass. And if we look at the code coverage, which is often used as a metric for the quality of your tests. So a lot of teams and companies boast about the high percentages of code coverage they have in their test suites. So this small example, this single test provides 100% code coverage for the code that you're seeing in the top left of the screen. Now imagine it's Monday morning and your developer comes in and they start refactoring and they didn't really sleep all that well on the weekend, and at some point they introduce an error to the code. Of course, they're not going to do this on purpose, but things like this happen. So they refactor the implementation of this is a powerful car method to always return false. Again, accidentally, not on purpose, but these things happen. And we've got our tests as a safeguard for refactoring and as a way to remain confident about the quality of our code and of our application. So they run the test again, it still passes, and even better, it's still 100% code coverage, so everything is fine. They check in this new version of the code into Git, for example. It goes through all the stages of a delivery pipeline, and as soon as it hits production and an end user invokes this code, they immediately see that something is wrong. And again, this is a very trivial example, but this is exactly how false negatives come to be and how code coverage is a flawed metric when talking about the quality of your automated tests. So as Martin Fowler said it, test coverage is a great way to find untested code, but as a quality target in and of itself, it's pretty much useless. So now that we've seen how tests can deceive us through either false positives or false negatives, how do we actually build trust in our tests, or how do we regain the trust that has been lost in our tests? To me, that all comes down to testing your tests. We are testers. We often write code that can be test code. Sometimes it's also application code. And we spend a lot of time testing application code because we don't trust ourselves as a developer, or we don't trust the developers in our teams, which is a healthy attitude. But we don't do the same with our own automated tests. And my recommendation would be to start doing that as soon as possible. Start testing your tests. And it can be as simple as doing code reviews for test code. We do this a lot for our application code. Either it's baked into the process using pull requests, for example, or we do it when pair programming or mob programming, there the code review is baked into the activity. Another good way of testing is just periodically go through your test suites, and for each test in there, just ask yourself, and again, you can do this individually or as a team activity, is this test still giving me value? First of all, is this test still useful? Is the information that this test gives still valuable for our team, for our product? But also, can this test still fail? Is this test still reliable? Is the information that we give, can that information actually be trusted? So I'd recommend do a lot of those. Review your test suite often, because it doesn't really make sense to keep on building your test suite and building it and accruing this mountain of tests, which nobody really knows what's the value of the individual tests in that test suite anymore. And don't be afraid to throw things out. Yes, you've spent a lot of time and effort writing those tests, and yes, they may be the best written tests that one can find on the planet. But if they don't provide value, if they don't provide information that's useful to you and your team, throw them out, because you don't need them anymore. And one of the principles that I teach a lot when introducing people to test automation is never trust a test you haven't seen fail. If I write a test and the code compiles the first time and it runs smoothly the first time and it passes, I've learned not to trust myself. Yes, it could be that I got everything right, but I want to make sure. I want to be absolutely sure that my test can actually fail. One of the ways to do this is by subtly changing the application code and checking that my test actually fails, because I want to know if it picks up on that change that I've made in the application code. If that's hard to do or too time consuming, another way to do this is to just change the expected outcome of the test and see if it fails, and if it fails for the right reason with a useful message, for example. So at least I know my test can fail. My test actually checks that which I expect it to check. Now, this sounds like a lot of work, and that's true. But the good news is there are tools that can help you test your tests. And the technique I wanted to talk about here today, a technique supported by tools which helps you get insight into the quality of your automated tests, is mutation testing. So you might have heard of mutation testing before, maybe you haven't. But let me before we dive deep into the practical application of mutation testing and a demo of how this works in practice, let's take a quick look at what mutation testing actually is. So what mutation testing tools do is they insert small changes in your application code, or in mutation testing terms, they generate mutants. A mutant is a copy of a specific method or a specific class in your application code with a small change. So that can be an inverted Boolean in a condition, for example, or a change in a comparison operator, or maybe a call to a different piece of code that is removed. So these are just some of the changes that mutation testing tools can apply to your code. And the second stage in the mutation testing process is running your unit tests against the modified code. So what mutation testing tools do is they generate these mutants and then they run your existing set of unit tests against the modified code. And if your unit test fails, that's good news, because it means that your unit test has picked up on the change that the mutation testing tool made in your application code. So if there are mutants that are not picked up by any of the tests in your unit test suite, that requires an investigation. Maybe there's a unit test that just keeps on passing and that unit test is of low quality or maybe even unnecessary, or the piece of application code that is being changed is dead code or unnecessary code, or code that's just not executed as part of the unit test suite. And again, that can be a conscious decision because you don't always need 100% code coverage, but at least it's worth an investigation. So if your unit tests fail, good news. If the unit tests keep on passing, you might have some work to do. So there are a number of different mutation testing tools out there. For example, we've got PITest for Java, which is the tool that you'll also see in the demo in a couple of minutes. We've got Striker for JavaScript, C#, and Scala. We've got MudMud for Python, but there are dozens, if not hundreds, of other mutation testing tools out there. I just picked a couple of ones that are fairly often used, but that's by no means, this is by no means a full list of available mutation testing tools out there. So let's take a closer look at what PITest can do for you. Again, it's a mutation testing library for Java. It's actually one of the few mutation testing tools that's supported by industry. So a lot of mutation testing tools originated from the academic world. And a lot of those tools stayed there. They didn't really get adopted by industry. PITest, while it also originated somewhere in academia, it's one of the few tools that's adopted by the industry as well, which has also been used a lot in the industry. That's probably because A, it's open source and it's a tool that's really easy to configure. That's not true for each and every mutation testing tool out there, but PITest is easy to configure and easy to use. And if you want to know more about PITest, just go to pitest.org, and that website contains pretty much everything you need to know about the tool. Again, configuring PITest is pretty easy. It's available as a Maven plugin, so all you need to do is add it as a plugin to the build section of your pom.xml, and in the configuration section of the plugin specification you can configure PITest to fit your specific needs. So in the configuration section you can configure PITest. The only thing I've configured here in this example is the target classes, so which application code classes or packages does PITest need to change. And under target tests, where are the tests that should cover these application code classes? So, and then running PITest against your code is as simple as the Maven command that you see here. That generates a mutant, it runs a unit test against your mutant, and it generates a report on the results. So you see a small snippet of the report on screen here. So it shows you line coverage, which is regular code coverage, but it also shows you mutation coverage, which is the metric we'll be studying a little closer in the demo that's coming up right now. So let's have a look at how PITest works in practice and what it can tell you about the quality of your unit tests. To demonstrate that, I've created a small Java project with an account class which represents a bank account. An account has three properties: a type, so either checking or savings, a bank account number somewhere between 10,000 and 99,999, and of course a balance. And I've also defined a number of methods on this account class to get the account number, to get the account balance. I want to be able to deposit. I want to be able to withdraw. And I've defined a piece of business logic that says, well, I cannot overdraw on a savings account. And a method that can be used to calculate interest, but calculating interest only happens on savings accounts, so not on checking accounts. And I've also defined a suite of tests for this class that tests whether the account number that's generated is actually valid. It has some checks around deposits, around withdrawals and overdrawing to see maybe if exceptions are thrown, and also a parameterized test that deals with adding interest. So the first thing I want to see is, do my tests actually pass? So when I run these tests using Maven, I can see that 8 tests were run and all of them passed, and that makes the build a success. Let's now invoke PITest using the command that we saw earlier. So that generates the mutants, runs the unit test for each mutant, and checks if the unit tests actually fail. PITest produces a report in the target folder, which we can inspect in our browser. So we've got 95% line coverage, but only 74% mutation coverage. So let's look at the details. Here we can see this line, so this light pink color means that this line of code is not being covered by any tests at all. And these darker pink reddish colors mean that there's a surviving mutant in our test suite. And we see some more details about the mutations shown at the bottom of this report. So let's take a quick look at the not yet covered piece of code. So we don't have a test yet that tries to add interest to a checking amount and see if that actually throws an add interest exception. So let's add a test here, and what we are going to do is add interest to checking account should throw add interest exception. So this should be a check. This should be a checking account. We initially deposit $30 and then we check that calling the add interest method throws an add interest exception. So just to see if all of our tests still pass, which they do. We've now got 9 tests and they all pass. Let's now again run PITest to see what this does for our line and our mutation coverage. Let's have a look. So now we can see that our line coverage increased to 100%. And if we look at the details, we can see that this line is no longer marked in light pink, but it's green now, meaning that it's at least covered. So this line is at least executed by at least one test. However, we still have a lot of surviving mutants. Now I'm not going to address them all, but just to give you some insight into the types of defects that a mutation testing tool can find in your unit testing suite, let's look at the example here on line 33. So if we look in detail at what PITest changed here, what the mutation testing results were, we see that it negated the conditionals twice, and that made our unit tests fail. However, it also changed a conditional boundary, and that change was not picked up by any of our tests. So what it did is it changed this greater than operator to a greater than and equal to operator, and that change was not picked up by any of our tests. If we take a closer look at our tests again, we see that we have a test here that creates a new savings account, deposits $30, then withdraws $10, and checks that the resulting balance is equal to 10. In itself, that's a test that makes sense, but it's a test that does not pick up on this operator being changed from greater than to greater than or equal to. To write a test that also picks up on this, we need to test around the boundaries of this conditional operator. So we need to have a boundary value test. So an easy way to do that is by, for this example, is by saying we're not going to withdraw $20, but instead we're going to withdraw 30 and then check that the resulting balance is equal to 0. So let's quickly see if our tests still pass, which they should, because 30 minus 30 is equal to 0. And it is. And now run the mutation coverage again. Let's have a look at the latest mutation testing results, and we see that our mutation coverage increased to 79%. And if we take a closer look at the details, we see that this line, line 33, is now green because the negated conditional mutants were still killed, but now also the changed conditional boundary is killed, which means that the change that PITest performed, changing the greater than operator to a greater than and equal to operator, has now been picked up by our test. And as a result, we now have a test suite that's of higher quality because it picks up on additional defects that it didn't pick up before. Now, I'm not going to bore you with implementing tests for these mutants, these surviving mutants in the add interest logic, because if you would look at them in more detail, you'll see that these mutants survived when conditional boundaries have been changed. So these surviving mutants are due to the same lacks of boundary tests in our existing test suite. So adding more tests around the boundaries of these conditions would improve our mutation coverage score here. The final thing I want to have a look at here, and for those of you who paid really close attention to the mutation testing or the mutation coverage percentages for the first two test runs that we did, we saw that the first run gave us a mutation coverage score of 74%, and in the second iteration we got a mutation coverage score of 68%, while all we did was add another test to make up for that, to increase our line coverage score. The problem here is this line of code in our account class. It includes a randomizer, and randomizers by nature produce different values each and every time. Now we have a test in our account test that just generates a new account of type checking and checks that the generated account number is greater than or equal to 10,000 and smaller than or equal to 99,999. Now you might think this is a good test to have. It asserts that every time I generate a new account, its value is always going to be between 10,000 and 5 times 9. However, a test like this doesn't give you much certainty, especially because there's this randomization thing going on when generating the account number. Now, one solution could be to just write lots more tests, but the problem is because each test generates a new account number, each test generates a new unique value. So you need to write a lot of tests before you can be reasonably certain that your logic is sufficiently covered by your tests. And this just goes to show that mutation testing doesn't really work all that well when you have an element of unpredictability or randomness in your application code. While you could choose to write a lot of tests and see, well, let's see if we can get much closer to a full mutation testing coverage, to foolproof tests here. Another solution would be to just say, well, this is something that we don't want to be covered by our mutation tests. We don't want to include this line of code because it has a level of unpredictability. It has some non-determinism in there because of the math.random, and we want to exclude this from our mutation testing results. Unfortunately, there is no easy way in PITest to skip specific lines in code. So one solution would be to instead extract this piece of code into a separate class. For example, a generator class that says we'll generate account number. Here we go. And create a new generator class with a public static int here we go. And because this is in a separate class and we configured PITest to only look at the account classes that start with account and test classes that start with account test, and generator does not start with account, so this will be excluded from our mutation testing procedure. So let's quickly run the tests first just to see if we did our refactoring right. We did. We still got all passing tests. And if we now run PITest again, and have a look at our mutation testing scores, we see that we've improved from our previous 79% to 82% because this line of code is no longer negatively influencing our mutation testing scores. So, as you've seen in this demo, mutation testing tools can do everything that code coverage tools can do, but more. So, they actually give you valuable insight into the quality of your existing set of unit tests. And that's not something, as we saw earlier in the example that I gave with the Java code that I showed in the slides, code coverage doesn't actually tell you anything about the quality of your unit tests. Mutation testing tools give you much more insight into the quality of your existing set of automated tests. To wrap this up, a couple of quick implementation tips for those of you who want to get started with mutation testing. Don't mutation test all your code. First of all, it's a time-consuming process. And second of all, it'll probably generate a lot of noise that's not really important. A lot of false positives in itself. So a lot of information that well, maybe there's something wrong with your unit testing code. That's not really all that important. So pick a piece of code that's important to you, that implements some vital business logic, for example, and start there. Start small and see if mutation testing brings you any value. See what that value is that mutation testing can bring in your testing process. Again, it works especially well for algorithms, for business logic. Those are typically also the areas of your code that you want to test really thoroughly. Are my algorithms, my calculations, my business logic, is that all implemented exactly as I need it to be? And this is where you probably have spent a lot of time writing tests for. And this is also a good candidate to start with if you want to start with mutation testing, to see if those tests that you wrote are actually doing the things that you expect them to do. And if you want to try PITest out for yourself, all of the code that you've seen in the live demo is available on my GitHub site. So feel free to have a look there and try it out for yourself. And that's it. Thank you so much for taking the time to listen to my talk. If you want to get in touch, feel free to reach out via email or via LinkedIn. And I'm looking forward to get in touch.